Okay, so this is the paper I chose. Aleksey protested because he's burned out by AI for the last couple weeks, reading a lot of things and didn't want to do this, but I insisted because of Thomas Anderson, uh, very influential systems guy from UW and good team here. So Aleksey is in a cranky mood, and he wasn't too in love with AI to begin with, so this is going to be interesting reading session. Giving a
Oh
heads
yeah.
up. Okay, let's start reading, Alexei. Self-defining systems, and I'm wondering if this defining is has to do with the specification. Uh, might as well. Again, we are doing the blind reading, so we haven't read the paper, and we will read as we go. The extraordinary, and this is a long paper. This was t- how many
It's
pages?
like 14 pages or 12, 13 pages, but the font looks big. So actually, I think it may be shorter than it looks.
Yeah, we can. Yeah, 10 pages. We could do it. We did go through long papers before. The extraordinary growth in demand for data center and cloud services, fueled by rapid changes in new use cases, application architectures, and hardware technologies, poses substantial challenges to infrastructure system designers. Good. I like this part. It takes far too long to understand. I'm sure Alex also likes this part. This is a good take. It takes far too long to understand, integrate, and build the solutions needed to deliver on the potential provided by the build out of data center and cloud computing capacity. Huh, that's interesting. Okay, this is going into
Okay, what
this
is
is going
interesting?
into a good direction, Alexei.
Uh, uh,
Infrastructure and then trying to adapt to the new hardware or new capacities, whatever,
yeah, but
new
it can also
resources.
it
Mhm.
can also mean we're gonna have LLM tweak the configuration, okay,
Yeah,
to adapt to the
probably.
new
Yeah,
infrastructure.
yeah, probably. Let's see. Consider, for instance, how long it takes to exploit the strengths and avoid the weaknesses of new ML accelerators. Yeah, GPUs, ASICs, etc. Or how long to completely move a complex on-prem application or data flow into the cloud while meeting requirements for availability, security, and tail performance. Good. So far, I'm getting good signals. These are not unsolvable problems, given even enough time and a large enough research and development budget. The hyperscalers have demonstrated that it's possible to integrate new use cases and technologies into existing systems. I guess Google with TensorFlow TPUs is an example. However, the rate at which we can do these tasks imposes a speed limit on how effectively we can leverage the trillions of dollars of investment in data center infrastructure. And yeah, the investment is crazy. The high level of investment needed to optimize workloads also limits the types of workloads that can be supported well. Alexei, you read.
Ah, our goal is over an order of magnitude improvement in the agility of infrastructure development. What we
Okay.
call so the time to integrate TTI for new use cases and technology integration efforts take days or weeks instead of months or years. Our approach is self-defining systems, SDS, is AI native, aimed at leveraging the unique abilities of LLMs to accelerate infrastructure agility while compensating and masking their weaknesses.
Mm-hmm.
Although the focus of the project is on infrastructure, we believe our approach can also dramatically accelerate the rate of innovation by system researchers and workforce training.
Mm-hmm.
Agentic AI offers a different scaling law for systems development, what we call scalable agency. While human engineering capacity grows sublinearly with headcount, sure,
Yeah.
uh,
Brooks law. Uh-huh.
agentic workforces can, in theory, expand nearly instantaneously with available compute.
Hold on. We believe this. I would say that with agents, the more agents you get, it's like sub linearly or something, right?
No, no.
So something gives. Hmm.
Uh, uh,
Because they
uh,
make a bigger mess. They make a
no.
bigger mix. They yeah,
I agree with this statement. Okay, this statement
okay.
says if you put a million monkeys in front of a typewriter and give them a million years, one of them is going to type something meaningful, right?
Mm,
That's what it says. It
okay,
doesn't
in
say that.
theory, I can buy this part.
Yeah.
Agentic work for in theory, and but I'm going to say that they do a bigger mess than
No, okay,
people
Murat.
do. They need more time. Maybe they don't need more time to catch up. Maybe that's there. They need less time to
I
catch up.
I am willing to bet
Hmm.
that the way this paper approaches agentic things is just like every other systems let's use agent paper does so, okay? Which will be let's start a bunch of agents on the same task with slightly different inputs and whatnot,
Hmm.
and see which one makes meaningful progress and then iterate from that. Right? We already seen this in
Yeah,
like
yeah.
this address paper and whatnot.
Right, right. But
So in that
that
regard,
thing works on a closed component, one component. Nobody got it to work on integration of components, and
uh,
they seem to target integration of components. That's what they say, infrastructure agility, right? So there should be
Yeah,
multiple
okay.
components.
A slightly different problem, okay? Instead of write some code, changing configurations, right? Adjusting some other codes.
So you are saying maybe this is still a single
I am saying that
monolithic thing. Hmm.
I'm saying that it may not be a monolithic in the sense
Yeah,
that,
yeah.
okay, look,
No,
head
I'm with
count,
you. Okay.
when you go for head count, right, people have to work together. You don't
Yeah,
throw,
yeah,
you don't hire
yeah,
100 people and tell them to do the same job, right?
yeah.
And then see who wins. You don't hire
Mhm,
100 people and divide them in 10 teams of 10 people and give,
mhm,
all of them the same job and
yeah,
see which one
mhm,
achieves it. But with AI, with agents, you can
mhm,
do this, right? You can build a pipeline. One agent is doing one thing, passes it to
mhm.
another agent that does something else, passes it to another agent that does something else,
Yeah.
and then you can do 100 of them and see what sticks.
Alex, you are defending the paper for me, but let's keep going. Keep
Well,
keep
okay.
reading. Keep reading. This agentic capacity.
Um, okay, so agentic
This.
workforces can, in theory, expand nearly instantaneously with available compute. This
Mm,
elastic agentic capacity enables thousands of design and integration
yeah.
hypotheses to be explored in parallel. Oh, see?
Yeah. Sure. Sure.
Provided we can also scalably compensate for their weaknesses.
Yeah. This part is okay.
Mm. Yeah. Our research agenda is to enable scalable agency to match the pace of hardware and workload evolution without being bottlenecked by human availability.
Okay. Enable scalable agency. This is what they call scalable agency. To match the pace of hardware and workload evolution. Okay. So it's a tuning system. Um, right? It's configuration tuning without being bottlenecked by human availability and targeted for infrastructure. One thing is like Brooks law for agents. That's an interesting topic of investigation. I think that's an interesting one. Okay, you read or I read? Keep
It's
reading.
your paragraph.
Consider what is needed to move a complex enterprise application into the cloud. Oh yeah, one. But this is a good problem. If they can solve this, this is a great problem to solve. Everybody is trying to do. One might start with a high-level English description of system components and objectives. Excuse me. Are we rewriting?
We are moving.
These need to be mapped into a formal specification, such as Terraform, and then what is Terraform?
That's the way you specify the hardware, like in a cloud. So you write this Terraform specification, and it
Mm,
can like spin out all the
mhm.
instances and networks
Yeah.
and like configurations for whatever cloud you
Okay.
target.
And then translate it into specific choices as to where and what specific cloud resources to select to meet objectives. A level below, configuring the load balancer for some specific critical element of the application requires understanding the workload. The configuration options of off-the-shelf tools and the option of introducing application-specific work assignment for greater efficiency or failure resilience. At every level, expertise is needed to generate plausible options, to instrument application data flows, to gather evidence, to sort through and evaluate these options, to model the likely effect of server and network failures and the performance interference from multiplex resources, to generate code to put decisions into effect, and to add monitoring to ensure that the application continues to meet its goals after deployment. Yep, the whole shebang. There is a lot of rewriting. Um,
What they're saying is there is a lot of people.
Yeah, and a lot of things to get right. You are making it, maybe this is distributed, but you are still getting it into a very elastic, more distributed environment. Okay, of course, this is just one example. Similar challenges arise for LLM runtimes, microservices orchestration, scientific applications that use custom accelerators, and data centers for specialized workloads. Okay, I like it. Your turn.
LLM-powered agents are both a use case and a potential solution. LLMs offer cheap relative to human, but buggy and approximate hypothesis and code generation, equivalent to having an army of inexpensive, tireless, and somewhat clueless junior developers. Okay, here goes my monkey analogy.
Code monkeys.
Industry already knows how to reduce the error rate of junior developers by limiting the scope and complexity of any assigned task. In places, existing systems are already designed with limiting interfaces, such as the use of Linux eBPF or sidecars in microservice architectures. In networking, we often rely on protocol encapsulation to avoid or isolate feature interactions despite the added overhead. In most technology integration efforts, however, we are forced to rely on expert experience, judgment, and code reviews to bridge gaps and avoid corner case behavior with the unintended consequence of slowing down the technology adoption.
Yeah. And you need a year and a half.
Mm.
You need a lot of time. Uh, Things work slowly just to get everybody on the same page. That requires a lot of communication, a lot of repeating yourself, a lot of training, etc. And a lot of trying to circumvent the telephone game, lossy, lossy channels from hop to hop. How do we build data center and shared cloud infrastructure for extreme rates of change? This means designing systems from the ground up for composability, simplicity, and rapid change, while preserving the key benefits of data center and cloud computing. Security, reliability, manageability, and resource sharing remain first order considerations. To make this vision a reality, we need advances on a number of fronts. Our approach is to deep dive into multiple case studies in parallel, abstracting back to common themes and design patterns. Hmm. We also plan to proceed from simpler to more complex tasks with an intermediate goal of producing useful tools for today's practitioners, researchers, students. Examples of needed infrastructure include specification languages for automatic validation of LLM code. Okay, nice. Systems architectures that support the safe insertion of small amounts of measurement and optimization code, observability, spec, and correctness. Okay, observability for performance. Simulation frameworks for offline hypothesis testing. Aleksey, this is you. And anticipating edge behavior, metastability.
Yeah.
As well as multi-agent systems for automating the hypothesis code experiment and analysis loop. This is good. I mean, we haven't seen agents do system design, and they are trying to say that's. I don't think this is full system design, but a step toward that. Okay.
Well, I don't think they are going for system design. I think it's still an integration problem, right? Like they're trying to solve
Yeah.
the integration hell.
Yeah, they called it infrastructure what? Infrastructure change or adaptability or something.
Yeah. But you know that's the integration hell part of the problem. You have a
Mhm.
bunch of components, right, that work in one place. You need to make them work in another place, so slightly
Yeah,
different
yeah, yeah.
hardware,
Yeah, still.
right? So it's not system design.
Mhm.
I mean, that being said, right? Like the other day, it's kind of off topic, but maybe on topic, right? The other
Mm,
day, um, I was playing with Claude,
mm,
and in about an hour and a half or so, uh, it wrote me a semi-decent sharded um, store with two-phase commit and two-phase lock-in
mm,
for transaction orchestration.
mm.
Again, like not designing new things, but for like known primitives, known like algorithms and approaches, it didn't like it did a decent job.
Okay, your point.
Recent work has shown that AI can help discover and implement better heuristics for core algorithmic components of complex systems. Do you want to look at those citations or
I think I know. These must be the Berkeley guys. Mhm.
21, 5, and 7? 21
25.
is a codes and agent for scientific and algorithmic discovery.
Okay, Alpha Evolve. That's Berkeley guys also
Yeah.
cited it. 5 is
Number 5
Berkeley
is
guys,
barbarians. Yeah.
Barbarians paper. 8 is Gilia, MIT guys. We haven't read this. A human-inspired AI for automated system design and optimization. Again, 2025. Like, what are we doing? All our references are the same year going forward. Okay.
Um, okay, yeah. So we take inspiration from these successes and argue for developing entire systems, starting from their high-level specifications and also closing the loop with their deployment and operations. Okay,
See,
entire
system
systems.
design. Yeah,
We have recently developed some relevant prototypes, such as specification languages and optimizing
compilers.
compilers for microservices and approximate performance models for tail latency and energy consumption,
Let's check these things. 41,
15 and 22.
41 is Thomas Anderson is there.
Hotnets 23,
Hotness 23. Application defined networks. Okay. 15 and
15.
22.
uh,
Again, Anderson M4. A learned flow level network simulator. 22 is
The case for
again
cloud
the
power control
tempo
plane.
case for a cloud power control plane. Okay, networking work. Specification languages, in this case, is this networking related?
Mhm.
Is this, yeah, scope to networking?
But there is much more to be done. In our view, the only thing that can keep pace with the rate of change of AI is AI itself. To make the integration and troubleshooting of new technologies automatic with human ingenuity only involved to set up an architecture capable of leveraging scalable and automated exploration of systems design space.
You know, this is how we get Skynet. Ah, example
Or
use
we
case.
wait for the bubble to pop, and then the rate of change is going to slow down.
I don't think the bubble is popping.
The bubble is popping.
Example use case. I think we are going to be seeing a bunch of use cases and then some conclusions. Huh? Let's look at the section structures. Section 2, example use case, self-defining LLM runtime. Oh, this is a case study that we will use, I think. 3 is overview. 4 is a path from here to there. 5 is research challenges remaining. Six is ongoing work, self-defining LLM runtime case study, another case study. Okay. No, the same case study, self-defining LLM runtime case study revisited at section 6. That's odd. I guess we are seeing this case study, then we are going to see um, the problems made concrete through that, and at the end, we are going to discuss what they have been doing with the case study. Section 7 is additional use cases uh, and related work and summary. Okay, let's read. To illustrate the challenges that self-defining systems, SDS, aim to address, consider the problem of building and maintaining an LLM inference runtime. The software layer that manages GPU memory orchestrates batching and caching and coordinates requests across heterogeneous accelerators. Is this a distributed system? Is this a system of systems? Yeah, there is batching and caching and request orchestration and a hardware part as well. This layer evolves at a remarkable pace. Every few weeks, new attention mechanisms, kernel fusion strategies, or distributed inference methods emerge, each requiring deep manual integration into the runtime. The process of adapting to these changes remains labor-intensive, brittle, and dependent on scarce expert knowledge. Your turn, Aleksey. Hold on. You keep reading, I'll become.
The key difficulty is the growing mismatch between the rate of innovation in AI models and hardware and the capacity of humans to re-engineer complex infrastructure in response. Modern runtimes must balance multiple, often conflicting goals, maximizing throughput while respecting GPU memory limits, avoiding contention across concurrent users, and ensuring reproducibility and correctness under changing models and workloads.
Mhm.
Even small design adjustments, such as modifying KV cache layout or tuning the batch size, can cascade into performance regressions or unpredictable inference across concurrent tenants. Humans spend enormous effort exploring design options, debugging solutions, and validating improvements.
Pesky humans.
Yeah, gosh. Um, SDS reframes this challenge by treating the runtime as an adaptive system that proposes, evaluates, and refines itself.
Yeah.
AI agents hypothesize design variants, generate code, conduct experiments, and analyze results based on high-level goals. Using a mix of simulation, live evaluation, and A/B testing, they explore a broad design space automatically, identifying trade-offs and converging toward systems that meet specified goals.
I'm getting mixed signals, like entire system design and tuning. We still have not resolved
Mhm.
this thing. It's still ambivalent. Okay.
Over time, the runtime learns
Oops.
how
Sorry.
to evolve alongside changing models and hardware to compensate the TTI for new ideas from months to days, to
Yeah.
compressing TTI for new ideas from months to days.
Yeah. What was TTI again?
Time to
Yeah.
time
Time to
to
integrate.
yeah.
Time to integrate. I like to figure.
Why?
Overview. Figure 1 shows an overview of the SDS approach for our self-defining LLM inference runtime. SDS first iterates with the user to get an appropriate spec of the system. The initial user input will likely be ambiguous or incomplete. SDS helps the user make it clear and complete, which includes external API, POSIX, the system can invoke. What do you mean? I don't know.
I think what they're trying to say is people talk in English or whatever language
Hmm.
you talk. You come up with incomplete specification in
Yeah,
ambiguous
no, I get it.
human
I don't
language.
get what POSIX is about.
It's an example, right? And then you refine like what APIs or what things you can use in the implementation in a system.
Okay. Okay. SDS then successively refines the spec toward a runnable system. Stepwise refinement, Dijkstra's idea. Hmm. uh, Dijkstra was going with proofs and proofs of refinement all the way. Um, The first stage refines the spec to system architecture, which outlines the modules of the system and how they connect. Its output is a document similar to the one that system architects produce today with module interfaces. The second stage refines the architecture. Okay, first stage. Um, and adds algorithms used by various modules to implement their interfaces. Its output is a set of design documents similar to those that senior engineers produce today. The final stage refines the design documents to runnable code. The artifacts produced by each stage are reviewable by humans. Initially, before the STS technology matures, we expect humans to review and possibly even edit the artifacts output by each stage so that the deployed system is exactly what we want. It's straightforward, maybe too straightforward. Yeah. Oh, but then you would have to have the feedback loops, right? See, the arrow goes both
Yeah,
ways.
yeah, yeah. Once you got the code, you evaluate the code and then you define it.
Hmm. And then this is where you could mess things up.
Right? So you say you like this diagram, and
Mm.
I dislike this diagram, right? Because it's actually missing the most important steps.
Which is,
It has the specs, but it doesn't have the evaluation step. What defines the correct behavior? If the spec itself is produced by LLM, right? Like, what
mm,
exactly defines the correct behavior of the system?
the spec. See, there is a arrow from deployed system to the spec.
Yeah, so deployed system, then it is being used to adjust the spec,
Yeah.
right?
No,
And also the
oh,
LLM creates the
maybe
spec.
this is not adjust. Maybe this is check.
LLM is used to create the spec.
Yeah.
See, the initial user input will likely be ambiguous and incomplete. SDS helps the user make it clear and complete.
Huh?
SDS then successfully refines the spec toward runnable system, right? So
Mhm.
SDS itself it is making the spec based
Yeah.
on the seed from the human, right?
Yeah.
So what defines the correctness of the system behavior?
Mhm. The spec.
Like I see no mechanism for you to refine things if you cannot define what is correct.
I think you are supposed to read the spec, agree on it, and then when the deployed system tells you I'm having problems here, you either
No,
adjust the spec or you say that no, fix it, get the deployed system, try again, get the deployed system satisfy this spec because this part is important.
it
And
says
I'm
initially
hoping the
before
spec involves something more than natural language like TLA plus, so we know what we are talking about.
that's not what they say.
We will see. Okay, your turn, Alexa.
Each stage has multiple possibilities. For complex systems, there tend to be multiple architectures with different modules that can achieve the same spec.
Hmm.
So see, like if the spec is concrete,
Right.
it will define the architecture.
Right.
They
Right.
bank on the ambiguity in the spec to
Right.
explore the space.
Yeah. So, what's the level of spec? Is it a very high level spec
Who
or?
checks correctness?
Yeah.
What are the safety properties? What? Anyway,
Okay. Let's keep
you like
reading.
the figure. I'm very disturbed here.
How can you put everything in one figure? I think this figure is good just to show the workflow. Okay, keep reading.
Well, the workflow is incomplete. It doesn't check for safety or for correctness. It just says, we're gonna run in a loop.
Let's read. The figure might be refined. Well, I don't see another figure actually.
Okay.
Okay,
Uh,
keep reading.
Similarly, for a given module, there can be multiple algorithmic choices, each with different implications for performance and other system level metrics of interest. Finally, there are multiple ways to implement a combination of architecture and algorithmic choices. One could do a microservice-like implementation where modules communicate via RPCs, or a monolithic implementation where all modules share a binary. SDS agents hypothesize refinements at each stage and evaluate the resulting artifacts. We discuss hypothesis generation and evaluation in more detail later, okay? But mention here a few facets of the evaluation process. One, evaluating the artifacts at upstream stages is more resource efficient but coarser. For example, architecture evaluation cannot benchmark performance, which depends on algorithmic choices and code as well. The goal of upstream evaluation is to rule out non-viable options early. And two, evaluation at the refinement stage informs future hypotheses at that stage, as well as upstream stages, backtracking. These two facets mirror how humans design systems in an iterative feedback-driven manner. Architectures that are deemed poor are not flushed out, and if an architecture that appeared promising earlier in the process later turns out to be too complex to implement, it is modified or discarded. 3, because each refinement stage can generate many independent hypotheses, SDS dynamically scales its population of reasoning agents to match the complexity of the design space. During early exploration, agentic capacity expands to cover diverse alternatives. During convergence, it contracts to focus resources on promising configurations. The result is analogous to autoscaling in cloud systems, but applied to reasoning rather than compute.
Yeah, I mean, this talks about this is how humans do it, but from what I saw, there was already a good design to get started with, and then we distribute it to teams, and then each team then does things, and these things are generally smaller modifications, like how do you implement a journal to be more throughput efficient, like with multiple journals, etc., rather than especially for a system, complex system, you always have a design in mind. You don't just go, oh, I have a spec and let's try architectures, and for architectures, let's try algorithms. You already have an, you already have a, you already have these nailed down.
Well, again, like that assumes you have an expert, right?
Yes,
Who
exactly.
spends
Right.
time.
Yeah,
But in 20 years from now, there will be no expert.
then we will be doomed. Okay. SDS agents also close the loop on operations and maintenance. They observe how well the system is performing in practice, compare against expectations, develop as part of the evaluation, and look for opportunities for improvement. They may realize, for instance, that most queries requests are short-lived and are better served by a different algorithm. Oh, how are you getting this real request when there's no system? Based on such observation, how do you have access to real workload?
I mean, you run the system, right?
You get the users to it.
Yeah.
Based on such observation, it may update the spec and then regenerate code. Spec updates supporting a new accelerator may come from the user as well. Read it, Aleksey.
The spec and intermediate artifacts are kept in sync with the running code, and all system updates start with spec changes. This helps lower TTI for new components. Today, when adding a new component, the bulk of the effort is not in writing new code for the component, but in ensuring that code changes do not cause collateral damage. Starting from the spec, and current artifacts and rerunning the same evaluation make it easy to make such judgments. It also makes it possible to generate small changes to those artifacts that meet new spec, which lowers the risks and makes changes reviewable by humans. Of course, there is nothing stopping users from providing code changes to describe spec changes. In that case, the system interprets the modified code as a proposed update to the specification and regenerates the intermediate artifacts to maintain
Okay,
consistency.
new components could be hardware, software, etc. And then the system adapts to that. That time I may buy better once you have a system in place, design in place. I mean, I have seen this as a spec and code drift problem.
Yeah.
But I guess they are saying when you have LLMs, when you could easily write code. Maybe my takeaway from this is like spec code drift, LLMs can help. That's
So so
the
so
that's
so
the pitch.
yeah, like again, like I understand this, right? The previous couple paragraphs, um, where like the user talks to
Mm.
LLM and then it turns out
Yeah.
everything, right? That
Mm.
that that just sounds to me like using a brute force, right, to replace the expert knowledge.
That's a bit unrealistic, but what I buy is after I have this with LLMs, we could have a good TTI, time to integrate, as they say. I can buy this better than the
Yeah.
initial system design.
I mean, I'm not saying like what they say, like the brute force method is unrealistic. I mean, it's all the matter of how many GPUs you have. If you buy
Mhm.
a year worth of NVIDIA GPU production, maybe you can do that.
I mean, you better have good prompting, good guidance to the agents, otherwise, brute force, you can't get monkeys to write
Yeah. Yeah.
Shakespeare.
I mean, again, like I am AI skeptic, right? But coding agents are surprisingly good.
When you prompt
Yeah.
it well, when you
Yeah.
guide them. Yeah. Okay. Multi-stage refinement and closed-loop improvement sets STS apart. Oh, self-defining system. Okay. From prior AI-driven system design efforts. Okay. This stepwise refinement and closed-loop improvement. Come on, closed-loop improvement. Everybody does that. It doesn't set you apart. Um, from prior AI-driven system design effort, whose insights we build upon. Prior efforts like Alpha Evolve and Address from Berkeley focus on generating code for a particular module given its interface and evaluation function. AI is not provided the context within which the module operates, which means the humans must still create and optimize the system architecture and module interfaces. The STS approach can be applied not just to new systems but to existing ones as well. I buy this one better. For applying it to existing systems where only code may exist, we can use AI to infer the intermediate artifacts and spec. I like it. And then hand over the system operation and updates to SDS agents. Oh, we have multiple agents.
Well, yeah, it's a brute force system, right?
Mhm, mhm. Okay, your turn.
I passed from here to there. Gosh, that sounds like Dr. Seuss. Um, we envision a five-phase progression that transforms agents from passive optimizers into autonomous system architects and operators. While we ground the roadmap below in LLM inference runtimes, the same pattern generalizes to other systems. Each phase represents a deeper level of autonomy and reasoning capabilities, progressing from low-level tuning to meta-level self-improvements. Together, they form successive stages in the evolution of self-defining systems.
Phase one, self-configuring. Mm. In this phase, the agent is provided with the system model and must tune parameters to meet objectives such as throughput or latency. It manipulates configuration values, simulates and experiments, and reports optimal configurations. For the LLM runtime, this means adjusting batch sizes, KV cache parameters, and memory pool sizes under varying workloads and GPU memory limits. Evaluation metrics for this phase include reduction in human tuning effort, fraction of automatically validated configurations, and performance parity for improvement versus expert baseline. Okay, I think I see where this is going, and it's like again, maybe it's better to do this layered, right? So try to do what you are given at the lower level and get the most
Mhm.
first. And if it doesn't work, pass a signal to the next layer saying that change something because this is how much performance I can get with this current design. Then I
Uh,
can go back to
it,
phase one and do it again.
no, Murat, phase one, phase two, phase three is the evolution of system. The first version of system can only change configurations. The
Yeah, yeah, no, no,
second,
no. Oh,
it's not
but
about
but
you
I
try
think this should be
configuration.
also layered because if you do this all at once, you are messing up things.
No, what they're saying it's a roadmap. It's not the architecture of SDKs.
Again, but I'm still thinking that this works better layered than um, all of them different agents messing up different parts because then we will never know.
But again, that's not how they will work. That figure that you like,
Yeah,
right? It's
no,
not different agents. It's a sequential thing, Something does a spec, something does architecture, then other agents do algorithms, maybe for different components of architecture, right? So it's a sequential process.
yeah,
They're
but
not messing with each other.
right, evaluation is missing, and now that's showing up more sorely here. And but again, I'm saying that a layered approach is the right thing to do here as well. I understand um, they are describing evolution of a self-defining system, but I believe it should also be layered, and then once we exhaust the layer, we get the next layer to change things up, and we try.
Again, I would strongly disagree with that, simply
Mhm.
because if you cannot, like, again, if you go with layers, like, try small things, right? And this didn't succeed, then try bigger things. Well, the reality is you may need to try both small things and bigger things to succeed, right? It's not like exclusive.
There should be a direction. We change the higher level, then we exhaust the lower level thing, and we give up and trigger another change at higher level. Is my proposal. Okay, let's read.
So this has nothing to do with the architecture, though. Just,
Sure. Your turn.
what are we at? Self-assembly.
Uh-huh.
Phase two, self-assembly. After mastering configuration, the agents learn to compose architectures from modular components. It receives a library of schedulers, cache strategies, kernel designs, and must select, interconnect, and tune them to achieve a goal. For example, it may pair a specific KV cache design with a priority-aware scheduler and test the design in simulation.
Hmm.
This phase expands the design space while retaining safety through modularity. The self-configuring capacities of phase one are used to tune each chosen module. Evaluation metrics for this phase include breadth of design space coverage within a fixed compute budget, aggregate performance improvements, and cross-component capabilities and reuse across runs.
Compatibility. Okay.
Where is safety? Again, the evaluation metrics are performance,
Yeah, yeah.
comparability, safety.
Yeah. Yeah. I don't know. Maybe self-designing. We will see. Self-creating. In this phase, the agent gains creative autonomy. It may propose and implement new runtime components or abstractions. This is like levels in engineering. You start as a junior engineer, become more senior. In this phase, the agent gains creative autonomy. It may propose and implement a new runtime components or abstractions. Using evolutionary or reinforcement learning approaches, the agent generates and evaluates hypotheses. For example, it might invent a hybrid KV cache that blends prefix and embedding-based reuse, synthesize the code, and benchmark its performance. Evaluation metrics for this phase include novelty and diversity of validated designs and speed of convergence to Pareto-optimal configurations and improvement over prior human or agent-generated versions. Your turn.
Self-designing. Um, The previous phases can evolve existing systems. This phase allows starting from scratch. Before an agent can design a new system, it must be able to describe it accurately. In this phase, okay, just a little thing, right?
Mm.
What is accurate description?
Spec.
Like TLA, like a concrete spec, right?
Yeah, we still don't know what spec is. We can.
No, because look,
Mhm.
if you think about it, like slightly higher level, right? The ultimate description of a system that is unambiguous is the program, right? Like the programming languages are designed to remove any ambiguity from language, from human
Yeah,
language, right?
yeah.
I mean, it doesn't mean that the programs are correct. We code all kinds of mistakes and logical errors in them, right?
Mhm.
But the computer will do exactly what the program tells you. It's unambiguous set of instructions, right? So when you say that something needs to be described accurately, well, yeah, it just needs to run.
Mhm.
Anyway, in this phase, the agent analyzes the user-provided spec, potentially referring to related existing runtimes, code-based execution traces, configuration files, to infer a machine-readable model of the system, components, dependencies, and data flows. For an
Mm.
NLM
Right.
runtime, this includes identifying the relationships between scheduling, memory allocation, kernel execution, and cache management.
Okay, we need at this point like concrete and concrete model of the system. Okay, what are these in? Is this natural language? And this says machine readable. What do we mean? What are these
This
interfaces?
phase, this phase establishes the declarative foundation that earlier phases can use to build and deploy the system description. The agent produces an internal representation that captures structure and constraints. Evaluation metrics for this phase include fidelity of the extracted model compared to ground truth, completeness of component graph, and correctness of dependency reasoning.
Phase 5, self-managing. Here the agents not only design new systems but also improve their own design methodology. Very interesting. It meta-learns which prompts, scaffolds, and feedback signals accelerate convergence. This phase closes the loop. Design processes themselves become adaptive artifacts. In the LLM runtime example, the agent might discover that structured feedback from the simulation traces yields faster improvements than raw benchmark scores and update its workflow accordingly. Evaluation metrics for this phase include rate of improvement in design, um, iteration efficiency, stability of learned scaffolds across diverse runtime families, and reduction in overall time to integrate for new ideas.
They're missing one more phase though. There has to be a phase 6, self-destruction.
Uh, yeah. This reads more like an SF proposal.
Actually, it doesn't.
Why
I
not?
mean, it reads like a proposal. I don't think it's an SF proposal.
Hmm.
I mean, it has a lot of words.
See, the next section is research challenges.
Yeah.
This is what you have in an SF proposal. Okay, your turn.
When creating practical self-defining systems, there are challenges at each stage, at each of the stages in Figure 1, and at each of the phases progressing to a self-managing system. We outline some of these issues here. All agentic workflow. A key research challenge is determining the agentic workflow. Which agents do we need at each layer, and how do they fit together? This is similar to how we might construct a software architecture to modularize and isolate concerns between cooperating developers and developer teams. The workflow also has dependencies across layers, similar to how a product manager might call on the expertise in the engineering team in order to conduct a cost-benefit analysis for feature prioritization. A unique research challenge for SDS is scalability. Unlike fixed human teams, the number of active agents can fluctuate rapidly as exploration load changes, The workflow must support distributed context sharing, decentralized evaluation, and consistent decision-making across an expanding and contracting agent population. We must architect control loops that allow thousands of agents to explore, learn, and converge in parallel.
Holy cow. Alexey, you are tired. We need to have agents read this for us. And we just and they should self-manage and learn for us. And this yeah. When you were reading about this, like agents that needs to work together, like cooperating developers and development teams. I started listening to a new podcast. It's called Shell Game. Very interesting. You should also listen to this. Funny. Start from season two. The guy built some voice agents using Lindy, another company, and then he makes one of them CEO, a CTO, HR person, marketing person, etc. He has meetings with them, and these talk to each other. But you should see, it's very funny. They talk in corporate speak and they run in circles. They are not
Yeah.
able to brainstorm ideas. They finally, they brainstorm. One episode is how they brainstorm the title for the company. They fail spectacularly. The guy helps. The guy then actually gets a co-founder. This was supposed to be a um, single person company to prove a point, but he's a media person going into this, so no code, low code. He gets a co-founder, basically Stanford junior person who is a hacker, agentic system hacker, and he configures things for him. Things improve a bit better, like they design a logo, etc. Then they figure out what should this company do, and then again talking
Yeah.
in circles. And then he comes up with the idea. And then this is a big point where he drops the ball. The idea is a bogus idea. The agents will be procrastinate on your half. They would be surfing Reddit so you don't surf. Come on. There is no value provided. Okay. This is at this point become hype kind of thing. He's from the popularity of show.
Yeah.
He's getting money like NFT, pure hype thing. We are now on pure hype, and then I'm in episode 4 or something of season 2, and then they are trying to get more humans, like another intern hired to do things, and it's interesting. And we are talking about these actual designing systems working under each other because the agents dialogue with each other is very circular. It's very
Murat, have you noticed this in papers recently?
yeah. We keep seeing the
Have
same
you noticed this in like a
regurgitate.
lot of like text, reading news articles and stuff like
Yeah,
that? Like,
yeah.
I
This last blog post on cloud specs. I have found um, I have a Google alert. It said that my name is mentioned. There is this totally LLM generated thing which quotes this post several times and quotes me several times, but it's not saying anything. It's just a
yeah,
stupid LLM generated post on top.
since we're in this off-topic conversation, right?
Yeah,
Um, the last video of 2025, remember we did that caching paper?
yeah.
So the first comment on YouTube
Oh, I didn't look at it. What did it say?
called us AI slop.
What?
So you and me, we are AI slop.
They thought we are bots.
I don't know, man.
Is this guy a bot or something? Let me look at it now. Yeah. Okay. Rethinking the, is this, yeah, rethinking the cost. They said we are bots. We have videos. Good discussion. Okay. I, for one, believe expecting implication. Okay. So stop AI slap. Who's Captain Memo? The opening sequence. What are you talking about? Who are you?
Cube. The opening sequence introduces a prologue. After this,
I'm... Probably
So
this guy
anyway,
or something. What the hell is
and that's why I don't want to
that?
read anything about AI.
This paper was not about AI.
No, no, this paper
Oh,
is,
yeah.
I'm fed up.
Uh,
Yeah,
Do
we're
we
on page
sound
five
do
of
we
this
sound
paper.
like AI bots?
Yeah.
Okay, yeah, holy cow indeed. Thousand agents working under each other. This is going to be chaos.
Likewise, we want the workflow to enable agents to improve over time. Both human engineers and computational models can be much more accurate and effective if they calibrate themselves against real-world experience versus run open loop. This learning can be from human expertise when there is a human in the loop, or as a result of later stages that validate and evaluate an approach. At any stage of the workflow, we can ask each agent to produce both a strategy and an estimate or prediction of how well that strategy will work when filtered through downstream stages of the pipeline.
You can't. I mean, there is so many uncertainty, so many parameters.
What is an effective architecture for agent-to-agent cooperation and mutual learning? Question mark.
I don't know. This is very hard question. Yeah.
Okay, my call AI slop agent. Your turn to read.
Formalizing the objective. Oh, specification, formalizing the objective. Okay. AI agents work best with a clearly articulated goal, but systems development is inherently multifaceted. As David Patterson once said, be careful what you choose as a benchmark, as people or AI agents will optimize for it. The systems research community has long had an intense focus on performance to the exclusion of all other concerns. A recent study showed that a third of the system research papers are solely concerned with performance, including this paper. Where is correctness? Yet simple performance benchmarks can be deceiving, as performance gains are only relevant if they do not jeopardize other, more important concerns. System developers need to balance a large number of competing concerns: reliability, security, manageability, observability, agility, cost, resource efficiency, and energy usage and correctness. In addition to performance, much of the expertise that humans bring to system design is judgment as to how to make these trade-offs. Exactly. How does one specify the goal such that agents can produce an artifact that balances real-world objectives? Your turn.
See, not very detailed discussion on the specification.
Yeah, yeah. Maybe we skip ahead to see. Uh,
I mean, these are the
Oh,
problems to solve,
we
right?
haven't gotten anything concrete, and I'm hoping section 6 on the case study revisited is going to give us something concrete. Let's quickly go through this, okay?
Okay. Architecture,
High level, high level. Let's see.
hypothesis generation, component interactions, and use case specialization. Um,
Can we use AI to automatically generate architecturally sound combinations? No. These are all open problems, right?
yeah, so yeah, like they say, a lot of things is, new usages of the old things, right? So, LLMs should be good for that.
I mean, again, Alexei, this is the self-repeating pattern of paper writing. We talked about this in the outline. Now we are saying research challenges and finishing each of them with, can we do this?
Yeah.
I don't know, you tell me. Uh, Otherwise, why are we repeating the same steps? Efficient hypothesis rejection. Can we efficiently avoid? Oh God. Are we
Security
making LLM
robustness.
writing? Are we making LLM writing change how we write papers? Okay, security can. Yep. Can we use AI to help generate the infrastructure? No.
Hmm.
Yep, this is the recent Amazon bug. I'm looking forward to the bugs that the
Yeah.
algorithms write, concurrency bugs. Incremental update. All knowing when to move on. Okay, let's read this. Alexa, your job is to read this.
I am ready to move on.
Mhm.
Human engineered systems typically operate open loop, continue to refine and improve the system in the most cost-effective manner possible until high-level management tells you to move on to some now more important task. Because a self-defining system will operate at a pace much faster than a human development team, we will need the system to monitor its own progress to notice when it has reached the stage of diminishing returns or has become stuck, because the most effective plan can be implemented. And by lowering the cost of development, we make it cheaper to keep going. How do we build an agentic pipeline that can monitor itself?
Alexa, at least there is an answer to this now. Do you know about this? The Ralph pattern? Ralph is this stupid character in Simpsons. The fat, stupid, simplistic guy. The idea is that simplistic. So they write a loop saying while there is still credit, take the next three tasks or do it, and then
Yeah,
Ralph stops when it's run out of tokens and credits.
yeah.
So they call this Ralph pattern. It's very interesting. At least I have a solution to this. Knowing when to move on, use the Ralph pattern and move on when you are out of tokens. I don't think this would converge for non-trivial systems.
So their case study is vibe coding.
Okay. Ongoing work, self-defining LLM runtime case study. We are revisiting it, and I hope we are going to see some concrete things about what spec they use, what model, um, machine readable model they use, and
Murat, this
what
section
happened.
is 1 page long. You're not going to get
Yes,
anything out of
sure,
it.
sure, sure, sure. I'm still looking for something more concrete than spec.
The methodology
We,
paragraph.
we kept saying spec. What is spec? I'm looking forward to learning about that.
Okay, good luck with that.
As a case study, we are building the LLM inference runtime, described in section 2 from scratch, using AI coding assistance for all design and implementation. Not for all design and human involvement focuses on setting goals, structuring tasks, and evaluating. Oh, structuring tasks! You are guiding. Our motivating question is how effective are LLM-based agents at realizing the STS workflow when constructing and optimizing complex system components? To this end, we investigate solutions to the research challenges outlined in section 5. In particular, we ask, let's start answering. How should we structure the agentic workflow, roles, context sharing, control loops to scale exploration while keeping human oversight small? How can the workflow detect diminishing returns? How would it know when to move on? Uh,
It's the same questions.
yeah, well,
We measure time to first correct build, total iteration cost, and like, okay.
okay. Okay, let's methodology. Okay, it's getting less than a page now. Alex, your turn.
Inspired by Alpha Evolve, which, by the way, they quoted that, Alpha Evolve is not what they do. But,
What? What do you mean?
you know, two
Yeah, yeah,
pages
yeah.
ago, they said that, Alpha Evolve and address is so inferior to like what
Yeah,
we
yeah,
propose that,
yeah.
you should ignore it.
Mhm.
Now we are doing Alpha Evolve, right? Inspired by Alpha Evolve, we build an iterative hypothesis, evaluate, refine loop over multi-stage SDS workflow outlined in section 3.
Okay.
Starting from a user-facing specification,
Mm.
agents propose candidate refinements at each stage, and we evaluate the resulting artifacts with increasing fidelity as we move downstream. Upstream evaluation is cheaper but necessarily coarser. That's the exact same phraseology they used before. Aimed at rejecting non-viable options early, while downstream evaluation can trigger backtracking when later results reveal early design mistakes or infeasible choices. Our current methodology retains goal setting, architecture decomposition, and evaluation design as human responsibility, while agents take over much of the implementation and optimization work. Further
I
work will
mean,
be
look,
required to
look.
realize this full SDS
Goal
vision.
setting, architecture decomposition, and evolution design as user human responsibilities. What else is remaining? Like even spec is human responsibility, and these guys are good designers by giving a good. I mean, the spec is almost half the work, more than half the work,
Murat,
right? You need to have
they're vibe
these guys
coding.
have 30 years of system design experience.
Yeah.
I bet spec is going to be much more different than
Yeah.
freshman student
Yeah.
spec. The thing is like that famous anecdote about a um, caricature drawer, painter that draw something in 5 minutes, so in a minute, and the guy says, "Why am I paying $1,000 for 1 minute? You drew this in 1 minute," and he says, "I drew it 30 years plus 1 minute." So, uh, okay.
Yeah, I mean, look, they're vibe coding, right? They give prompts with the goals and they're vibe coding.
But
And
whose vibe coding is important thing. You
exactly,
need to
right?
have
So
that 30 year of experience
yeah,
lessons to be able to vibe code
yeah.
like this.
And when I vibe code, I kind of again, yeah, I do the same thing. I set goals, right? But like my goals are very precise. I
Yeah.
try to use the language that's like as unambiguous as possible. And like my goal setting for the freaking Claude code can be like huge like list of what I want to do,
Mm.
right? Like precisely. Anyway, um, the results of workflow lets us measure how different specifications and workflow structures affect TTI and iteration cost, and how well agents and select architectural algorithm, how well agents generate and select architectural slash algorithmic hypotheses. You can do the early results.
Ah, my flu is getting worse by the minute. Early results. So far, see, I'm not a AI bot. I have flu. Early results. So far, our case study has produced two working LLM runtimes. Almost V2 and a monolithic LLM runtime. Uh, Together, they let us quantify how far AI coding agents can go today. To do so, we evaluate all systems on a throughput benchmark Qwen3 model on NVIDIA GPU, GCP, VM using short blah blah blah. As a performance baseline, we use Nano VLLM, a simple but high performance LLM runtime that is compatible with and provides similar performance to the popular VLLM runtime. Our
Mhm.
throughput benchmark is what the Nano VLLM authors used to demonstrate Nano VLLM's performance parity with VLLM. Let's check this VLLM, Nano VLLM reference 6. Geek Explorer, et al. Nano VLLM, lightweight LLM inference engine. Do the specs also come from these projects? Like, you remember the Barbarians paper? We said that, oh, I mean, of course, the problems specification, the entire thing, even the evaluation comes from the previous papers they wrote. They are just
Mhm.
letting the AI agent use the scaffolding, the infrastructure, just to tune and improve things. And I'm wondering if it's the same thing. Okay, Alex, your turn.
Uh, to build Almost V2, we instructed the agent to base its design on Almost, a rudimentary and slow LLM runtime that we built using ChatGPT. we further instructed the agent to construct Almost V2 to reach the performance of Nano VLLM. Almost
See,
V2,
they already have a system in place.
yeah, Almost V2 reaches roughly
See, they are
1.
taking its design and building on it. This is from UW. They already have
Mhm.
all those scaffolding built, and it's iterating over the build thing.
Yeah. Then they build monolithic LLM runtime from scratch with a much shorter prompt sequence and less human structure.
Mhm,
So this is your example, right? So they say, I guess, from scratch, right? So not based
mhm,
on previous design.
mhm.
We intentionally, so they didn't provide the baseline system and asked the agent to keep the code simple.
53 times speed
Mm.
up since inception. It was a very dumb baseline to begin with. But okay. What's going on here? So almost V2 they tune. And the
Mhm.
other monolithic one, since it's monolithic, they built from scratch. Is that
Yeah,
right?
yeah.
Okay. Okay. Aleksey, you read, okay? I'm like very congested.
This prototype suggests that agents can assemble high-performance systems from scratch with little structure. Well, wouldn't you think that an LLM that runs, on those types of systems will actually know the code that it runs upon? Like people who design LLMs, they would definitely, train them on the code that runs LLMs.
Mm. Hmm.
Like,
Hmm.
anyway.
Okay.
For both runtimes, the development optimization path was largely agent-driven. Starting from a naive PyTorch baseline, the agent implemented flash attention, CUDA graphs, KV cache reuse, continuous batching, and prefix caching, and each contributed substantial incremental speedups, with CUDA graphs and KV cache reuse providing the largest gains. The agent also implemented page detention style block management and hash-based prefix caching, and learn to profile bottlenecks and reason explicitly about compute versus memory bandwidth limits.
Hold on. Okay, good. Development and optimization path was largely agent-driven. And again, Alex, I think this comes to your point. This is an existing system. The agent already knows the existing designs and just retrying them.
Well, yeah, they implement some all these, known techniques, right?
Yes, LLM inference is known technique, and when you ask ChatGPT now how you would implement an LLM runtime, it would give us similar things. Okay,
Mm.
nothing to boast about here.
Over time, we evolved from agent as code generator to near autonomous implement deploy benchmark loops. Our agent now routinely performs Git operations, provisions, and configures new GCP VMs, installs drivers and dependencies, runs benchmarks, and summarizes the results. A notable milestone was an agent-authored key solutions document that distilled past deployments failures into reusable playbook, cuts in end-to-end deployment from 90 minutes of human in-the-loop debugging to 6 minutes with no human intervention on fresh VMs.
Mm.
This allowed us to accelerate the development process from 35 days for Almost V2 to just 2 days for monolithic LLM runtime.
What's going on here?
Um,
Oh, almost
yeah,
V2. Why did it take 35 days? They are starting with almost.
yeah. No, because of the integration hell.
No, no, no. But they are saying almost V2 going from almost took
Yeah,
35 days. Why?
yeah, because of integration hells.
Because of integration hell. I see.
Yeah, right. So like installing,
Of
running,
course.
blah blah
Yeah.
blah.
Yeah, yeah, yeah. And then
So
the
so
monolithic one is easy. Sure.
Well, because by the time they already figure out essentially how to do everything, right? How to run the loop, right? The deploy, test, evaluate loop. Uh,
Hold on. I need to read this paragraph. Okay. The monkeys figured out how to get it deployed and tested.
Mhm. Which again is not really that, for an agent nowadays.
What is this 35 days thing? This is human guided, right? Human helps them, right?
Yeah.
Okay. They didn't keep this thing eating tokens for 35 days and trying things in a loop.
Yeah, I don't think that's what it means.
However, so far our agent failed to exceed none of VLLM's performance. It unsuccessfully attempted FP8 quantization, chunk prefill, torch compile, and custom triton kernels. I mean, if you had gotten nano VLLM and tuned it, you would exceed it. That's the address guy's approach. In these cases, our agent rediscovered techniques already subsumed by CUDA graphs or ran into subtle incompatibilities and workload mismatches, plateauing without proposing qualitatively new designs. Yeah, this is the story of the Shell Game podcast. Uh,
Do you want to go into additional use cases so we can
okay.
start wrapping up?
Microservices management, deploying complex applications in the cloud. Yeah, this is important use case, but good luck, buddy. I mean, if you solve this, you got probably a billion-dollar company if you could solve this automatically.
Mhm.
Scientific computing, specialized data centers.
So in the related work, they have a 5-line paragraph about formalization and specification.
Specialized data centers. This is also interesting, but I don't know if there's anything custom question. Let's solve the easier problem first, and let um, let's optimize cloud providers later on. Yeah, but yeah, initially this started like that, right? Infrastructure agility.
Mhm.
And we haven't heard of about infrastructure agility after that, right?
Yeah,
Because this was the idea, initial idea. Can we
that's
have
what it
this
seemed to me. Yeah.
specialized data centers? Yeah, there is a big mismatch about the introduction and the rest of the paper.
I mean, maybe the agent that was writing this paper got, lost the context window by the time it got to the end of the paper.
AI for discovery and program research, formalization and specification. What is auto formalization? 34. Auto formalization with large language models. I have no idea. I haven't seen this.
It's from 22. Large language models were not that large back then.
Uh, Efforts such as autonomous code evolution and text grad. 37.
37, another archive, automatic differentiation via
2024.
text.
Explore ways to make reasoning and optimization differentiable through text bridging natural language problems and formal objectives. I mean, this is good, but I have no idea differentiable through text. What does it mean? What is differentiable? But maybe this is where automatic differentiation via text. We're checking. AI-driven system design. I think we had a run on this. which argues that almost decades of AI research methods that leverage computation and learning ultimately surpasses those that rely on human insight and manual design. Sutton's motivation was epistemic. Systems will, in the long run, outperform humans at producing better solutions after humans solve those problems. The SDS vision, by contrast, is pragmatic. It arises from the growing mismatch between this. This sounds very LLM written.
I say we call it a day.
Okay, let's look at summary. Is the
Yeah.
summary harkening back the integration thing or not? I mean, in infrastructure, it doesn't, I guess. Nope. Cool. Okay. Uh,
What do you think
1.5 hours. What
about
do
the
you
paper?
think? I was initially very excited about the infrastructure tuning. I thought I would get something concrete, but even for the, spec thing,
Yeah.
what computer machine readable model is, we have nothing that I can hold. It looks like they did something similar to what Address did with LLM inference, and
Yeah.
that's. I mean, I really liked the initial vision, but then it failed to deliver on any of those, and not even getting close.
Well, yeah, my concerns are kind of, the same as in the beginning, right? Like,
Yeah,
um, it's like, to me, it's still the same approach as address and a
yeah,
bunch of other things,
yeah.
right? Throw agents, see what happens, evaluate, and rinse and repeat. But unlike address, this doesn't talk about how to specify or how to evaluate.